So a system of DEs might look like dx1 dt equals some function, let's call it g1, that depends on a whole bunch of different variables up to xn all the way up to dxn dt with some g of n, x1 up to xn. So we have n different independent variables, or dependent variables, x1 through xn, that all depend on t, x1, x2, all the way up to xn. Now, when we only have two of them, we tend to just call those, instead of getting bogged down in subscripts, we'll just call them x and y. We might say dx dt is 3x plus 4y, and dy dt is, I don't know, negative 2x plus 5y. That would be a system of two DEs. And this would be linear homogeneous with constant coefficients. But when we have a whole bunch of them, we kind of run out of letters, so we'll call them x1, x2, x3, and so forth. Okay, now, these functions, these g's, can be really complicated. But let's say we have a linear system that might look like dx1 dt is some a11 of t times x1 plus a12 of t n of t xn all the way down to dxn of t is a n1 and then possibly some extra functions over here, say some f1 of t all the way down to, say, fn of t. So this is linear in the fact that all of my independent variables, x1 through xn, they all appear just to the first power, and then there's stuff in front of them that only depends on t's. And we call all of these our coefficient functions. And then maybe there's even extra stuff here that only has t's in it and doesn't have any of our x's. Well, this could be rewritten in matrix form. Need the space, I'm going to erase this, but I'm rewriting exactly the same thing in a matrix form where we say our vector x is the column matrix x1, x2, up to xn. Our matrix A is all those coefficients, A11. That's why we numbered them like that, because they're matrix elements. Okay. Up to A1n, down to AN1, up to ANN. And all those extra functions at the end we call capital F. That's the column vector, F1 up to Fn. Then that equation I wrote just a minute ago could be rewritten as the derivative of this guy is A times this guy plus F over here. This is what we're trying to solve for. For this class, we're not going to do any nonlinear systems. The linears are bad enough. And in fact, for the most part, we're going to stick with homogeneous where F equals 0. So if F equals 0, the 0 vector, this is homogeneous. If F's not 0, it's non-homogeneous. Maybe we'll solve one of those. So we did the same way we did before. We solve the homogeneous version. We find a particular solution using undetermined coefficients, and we tack it on to the end. But we'll mainly focus on the homogeneous ones that look like this. Okay, so what do solutions look like? Solutions are vectors. So say we had let's write out an example first, and then we'll do one with the solution. Say we had dx dt equals 3x plus 4y. dy dt is 5x minus 7y. This is a system of two DEs. I have two dependent variables. They both depend on t. X and y are both functions of t. I want to eventually get to the point we can solve this. Well, first we want to write it in matrix form. So we call the vector capital X, little y. And you just got to get used to that. You got to get used to X, the symbol X kind of having two different meanings here. There's little x, who's one of our variables. There's capital X that stands for a vector. Now, if you read your books, writing these vector symbols takes a lot of work when you're typing that up. So what books will typically do is just make this bold. They'll just have bold X. That's a lot of work when you're writing with a marker to make stuff bold. So I'll use the vector symbol. Your book will make it bold.
Okay.
Then this system of DEs can be rewritten as the derivative of this guy equals this matrix 3, 4, 5, negative 7 multiplied by this vector X. Or X prime equals AX, where A is the matrix 3, 4, 5, negative 7. Okay. I think it's worth going through the trouble of literally writing all this out just to prove, to see this. Okay, so let's do that. So this here, X prime would be the vector little x prime, little y prime. I'm claiming that that's 3, 4, 5, negative 7 times the vector xy. Okay, so remember matrix multiplication is row by column, row by column. So I take this top row times this column, rotate it over, and add. So 3 times x plus 4 times y will be my first entry. That'll be 3x plus 4y. Then row by column. 5 times x plus negative 7 times y will be 5x minus 7y. So this now, this is a column vector, this is a column vector, this is a vector, this is a 2 by 1 matrix. Remember when you're multiplying matrices, this was 2 by 2, multiplied by a 2 by 1, you get the outsides. The insides have to match up. The answer is the outsides. So the outside is a 2 by 1, 2 rows, 1 column. This says x prime equals 3x plus 4y. Y prime is 5x minus 7y. That's exactly what we had to begin with. So this here is just a fancy way of rewriting this. What do solutions look like? Solutions are vectors. Prime is 1, 3, 5, 3, x. I claim that x1 is e to the negative 2t, negative e to the negative 2t, which could be rewritten. We could factor out that scalar e to the negative 2t. These mean the same thing. Here I've just written it in vector form. Here I factored out that e to the negative 2t, that's just a scalar, and that factors out of the matrix. I claim this is a solution. So let's check it. I'm going to check it in this form here. So I claim if I take the derivative, and that would be the same as multiplying by this matrix A. So let's do that. Let's take the derivative. We would get negative 2e to the negative 2t. We just take the derivative element by element, positive 2e to the negative 2t. Does that equal question mark 1353 times the original? Well, let's check and see. Row times column will give me my first entry. So 1 times this plus 3 times this. Those are like terms. That would be one of them. Minus 3 of them. That would be negative 2e to the negative 2t. For my next element down here, 5 minus 3 of them would be positive 2e to the negative 2t. And so it works. That's exactly what we said we were supposed to get. Now, let me point this out, by the way. This guy is also the solution. Let's call him x2. You can check this on your own. 3, 5e to the 6t. We're going to try to build general solutions, and for a general solution, you need the rank of your matrix. However many equations you have, that's how many linearly independent solutions you need to build the general solution. This was a 2 by 2, so I need 2 linearly independent solutions. Okay, now let's write this out in the standard form, just so you can really wrap your mind around what we're saying. Okay, so this really said, let's say, our variables are x and y. This first one says the x dt is x plus 3y, and the second one says dy dt is 5x plus 3y. That's the system we're trying to solve. I claim that this thing was a solution. Keep wanting to put a 2 there. Negative e to the negative 2t. That's just x equals e to the negative 2t, y equals negative e to the negative 2t. So we're saying if you substitute these two things into these two equations, both sides will come out equal. Take the derivative of x, that'll be the original plus 3 times this one. Take the derivative of y, that'll be 5 times that one plus 3 times that one. That's what we're doing.